As we start to talk about solving systems of linear equations, we want to first look at some basics about matrices to make sure our terminology is all the same. So, a matrix is simply an organized compilation of information in rows and columns. For example, here's a matrix which has 2 rows and 3 columns. So there's 6 entries total in this matrix. Now sometimes you'll see a matrix written with these brackets, and sometimes, I'll do it in a different color, instead of the brackets you might just see curved bars like that. And so it depends on the textbook that you're looking at, but they both represent the same thing. Okay. Now we say the size of a matrix is going to be how many rows by how many columns. So you want to make sure you have this in the right order. So this matrix in this example above is a 2 by 3 matrix, not a 3 by 2. So the first number represents how many rows, and the second represents how many columns. If I want to refer to a specific entry in the matrix, I'm going to use the notation E and then subscript with 2 numbers separated by a comma. So E sub 1 comma 2 means the element or the entry that's in row 1, column 2. So if I go back up here and make a nice arrow. Okay, so E1, 2, so the 1 represents the row, so that would be the first row here, and then the 2 represents the column, and that's these. So we want first row, first column right there, the negative 3. First row, second column, negative 3. All right, so that's the notation how we're going to refer to these. All right, so now let's go back to systems. Given the system of equations, so this is just a simple example, and I just had the numbers go in order so it'd be easier to refer to. 2 things that you should be able to do, and one is called the coefficient matrix, and it's exactly what it sounds like. It's a matrix that contains the coefficients of your variables in your system. So that's the coefficient matrix. 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the augmented matrix, that's the matrix that has the coefficients, and the last column is going to be the constants that are after the equal sign. So notice we're adding one more column for the augmented matrix. And so these numbers here represent each of my equations in my system of equations. And it'll be easier to do some operations on these numbers instead of having to write all the variables. And so the augmented matrix is what we're going to use to solve our systems of equations. So let's look at a couple of systems here. What if I asked you to solve this system? Well, you probably look at it and say, well, that's really easy. I don't need to do anything else. I can look at the last equation, and I can figure out what z is equal to. So that's going to tell me that z is equal to 1. And now that I know z is 1, I can use the second equation, plug in 1 for z, and figure out what y is equal to. So y is equal to 0. And now that I know z and y, I can plug those into the first equation, and then I can figure out what x is equal to. Negative 3x plus 0 plus 2 is equal to negative 19. So negative 3x equals negative 21. So x is equal to 7. So if I'm writing this as an ordered triple, I would write 7, 0, 1. And that's the solution to that system of equations. Now that's really easy, and I understand that. And so if we can make our systems, or put our systems into this form, which is called upper triangular form, then we can simply use back substitution to solve our system. So that's going to be our goal. Our goal is to get our system into this upper triangular form, and then we can work backwards and solve for each of our variables. So what if I asked you to solve this system? Well, this is going to take a little more work. It's not as easy. But what we can do is we can write the augmented matrix for this system, and then we'll put it in what's called row echelon form, which is that triangular, upper triangular form, and use row operations to accomplish this. So I'll show you what I mean by that. But first, let me define what these row operations are. What's legal to do, what's not legal to do. All right, so your elementary row operations, you are allowed to interchange two rows in your augmented matrix. And that should make sense because in a system of equations, if you switch the order of your equations, that's still the same system. So that should make sense. You're also allowed to multiply each entry in a row by a non-zero constant. Obviously, multiplying by 0 would cause a problem. It would change our system. But if you take any equation and multiply both sides by a constant, that doesn't really change the equation. It looks different, but it's still the same equation. And so likewise, you can think of this as division too if you're multiplying by a fraction. Let's say multiply everything by 1/2. Then that's really like dividing. So multiplying or dividing. And then the third one, and this is the one that we're going to be using the most to try and change what our augmented matrix looks like to put it into that upper triangular form or that row echelon form, reduced row echelon form. We can add a multiple of one row to another row. All right, so now I think we're ready to go ahead and try that. So here's the system. So step one, let's write this as an augmented matrix. And you know, those of you that don't like to write things out, this is probably going to bother you for a while, but it's really, really important because then if a mistake gets made, it's easy to backtrack and find where the mistake is. It's also easy for somebody who's looking at your work to figure out what you did. And so we have some special notation we're going to use as well. All right, so let's go with blank. Let's write the augmented matrix first. So we have a 1, a 3, and a 2. And then a 0, because there's no y term in the first equation, a 1 and a 2, -3, -2, 1. And then sometimes you'll see it as a dashed bar, sometimes just a vertical bar. And that's kind of tells you where the equal sign is at. And then -5, -4, -2. So there's our augmented matrix. Now the goal is to try and get these three numbers to be 0. Because then the bottom row will represent an equation z equals something, and the second row will be y plus z equals something, and then we can use that back substitution to solve. So always keep that in mind. The goal is to make these numbers 0. So what we're going to do, actually maybe, well, okay, I'll do it this way. So I'm going to use the first row to try and get zeros below it in the first column. So what I'd like to do is, first of all, I'm going to leave the first row alone. I'm not changing those numbers. So 1, 0, -3, -5. But now the second row, I'd like to change, and I want that 3 to be gone. I want that to be a 0. So if I multiplied the first row by -3, a copy of the first row by -3, and I added that to the second row and replaced my second row, that's the third of those elementary row operations that are allowed. So notice I'm writing this notation even with row 2 because that's the row that's going to be changing. So now if I multiply a copy of the first row by -3 and add that to the second row, I'm going to get -3 plus 3 is 0. This is why I'm doing it. I want that to be a 0. Then -3 times 0 plus 1 will give me a 1. -3 times -3, which is 9, plus a -2 gives me a 7. And then -5 times -3 is 15, minus 4 is 11. So I've modified row 2 using the operation of multiplying a copy of row 1 times negative 3 and adding it to row 2. Now, if you need to write this out on the side or on some scratch paper, for example, I was doing all that in my head. So I took the first row and multiplied by negative 3. So I had negative 3, 0, positive 9, 15. And then I added that to the second row, which was 3, 1, negative 2, negative 4. And that's where I got my 0, 1, 7, 11. Right there. Okay, so if you find that you're making mistakes trying to do it in your head, or if it's just too complicated and too much to keep track of, then just go ahead and write it out like I did here on some scratch paper. But what I do need to see is your notation for what was done to get to the next step. Now, I'm going to include two things here. So now let me do the same thing with the third row. I'd like the first number in the third row to also be 0. So this time I want to take a copy of the first row and multiply it by negative 2. And then I'll add that to the third row. And so when I do that, I'm going to get a negative 2 times 1 plus 2, which is 0. And then negative 2 times 0 plus 2 is 2. And then negative 2 times negative 3 is 6 plus 1 is 7. And then negative 2 times negative 5 is 10 minus 2 is 8. All right, so now I have an augmented matrix which still has the same solution or solutions as the previous one did, but notice that it looks a little simpler. So now I'm really close. The only thing I need to do to finish off getting it in that upper triangular form is to make that 2 a 0. And then I'll be able to use back substitution and solve. So, now what I don't want to do here is I don't want to use the first row anymore to modify the second or third row. Because if I do that, that first column, those numbers are not going to be 0 anymore. So I'm done using the first row. So now I'm moving on to the second row. And now I'm going to use the second row to get zeros underneath it in the second column. So what I'd like to do to get rid of that 2 is I would like to take a copy of the second row and multiply it by negative 2, and then add that to the third row, thus changing my third row. So my first row, scroll up a little, my first row stays the same, 1, 0, negative 3, negative 5. My second row also stays the same. And now the third row is going to become what? A copy of the second row times negative 2, and add that to the third row. Well, negative 2 times 0 is 0, plus 0 is still 0. So that's good. I want that to stay a 0. The second column now, negative 2 times 1 is negative 2 plus 2 is 0, which is why I'm doing this. In the third column with those 7s, I do negative 2 times 7 plus 7. So negative 14 plus 7 is negative 7. And then the last terms, the answers, so negative 2 times 11 is negative 22, plus 8 gives me negative 14. And finally, just to make my life simpler and to show one of those other row operations, I'm going to multiply the third row by negative 1/7 and replace that third row. So I've got 1, 0, negative 3, negative 5, 0, 1, 7, 11, 0, 0, 1, and 2. So now remember, what does this represent? Go back up to our system. We had a system with x and y and z. So now what I've done is I've transformed this using these legal rules to say x minus 3z equals negative 5, and y plus 7z is equal to 11, and z is equal to 2. So for my solutions, we know z is equal to 2, and then plug that into the second equation. Y plus 7 times 2 equals 11. So y is equal to -3. And then plug both those values into the first equation, actually only the z value I need, in the first equation. And so when I plug 2 in, I get x minus 6 equals -5. So x is equal to 1. So the solution to this system, if I write it in the right order, 1, -3, 2. Now, this may seem like a lot of work. Once you get the hang of it, and this is one of those things where the more you practice it, the easier it gets. And the first time through, you might have some difficulty, or it might take you a while. But the more you do them, the better you get. It happens very quickly. And then, even though this is only a 3x3 system, you can see that we can actually handle any size system. You could have 10 variables with 10 unknowns. 10 equations with 10 unknowns, and you'd be able to use these operations and solve it using back substitution. Whereas without this, I don't know if you would be able to figure out if there's a solution or not. So now you're ready to go ahead and do the problem sets, and then go ahead and submit those.